So for this one, if we have a look at the base case of 1, we would just be doing 1 on 2, and over the right hand side we would get 1 on 2 as well. So the base case P of 1 is true. Let's have a look at the assumption. So for some integral k, we're assuming that it's true. So what are we assuming is true? We're assuming that when I sub k in, so I've got odds on top, I've got evens on the bottom. When I sub k in, I get something that's greater or equal to 1 on 2k. And what are we required to prove? So this is what we're required to prove, that 1 times 3 times all the way to 2k minus 1, and then times, so that's the times, 2k plus 1, all on again, 2 times 4 times all the way to 2k, and then we're timesing by 2k plus 2, so we're subbing k plus 1 in there, should be equal to, greater or equal to 1 on 2k plus 1s. So let's take the left hand side of this one, let's pretend I've written it down, and what I'm going to do is all that section is use the assumption to fill that in. So now I'm filling in something that is smaller. So the top is now greater or equal to, once I fill it in, 2k, 1 on 2k times 2k plus 1 on 2, and that, factorise, 2 lots of k plus 1s. And you can see that 2 lots of k plus 1s is what I want. So the other part is 2k plus 1 on 2k. And that part we can see is clearly like it's 1 on 1 plus 2k, and remember k is positive. So, oops, that's, yes, 2k. So that is definitely greater than 0. So if I just take it out, if I just subtract it, I'm getting something that's even smaller, right? So that, if I just get rid of it and do that, that's going to be even smaller, and that is what we want. So yes, fill in a few more lines there, but then P of k does imply P of k plus 1, and P of n is true for all n greater or equal to 1 by induction.